Hello friends, this video on Redox Reaction Part 19 is brought to you by examfear.com. No more fear from exam. Now let's understand a very critical topic called titration. We use this pretty often in the labs. Titration is nothing but a process of finding strength of one solution against the strength of already known solution, right? Or also using pH sensitive indicators. So they call titrants or titrator, and you must have done something like this in labs. You have this pipe and you have some solution here and some solution here. You keep dropping little bit and keep mixing till the color change, right? So if there is a change in color, that means end point is reached and the one reaction is complete. And with that you can tell that this reaction needs for example, you have a reaction of A plus B is C plus D. You can say that this milliliter of and you have some let's suppose 10 ml of A, and then with reaction with dropping little bit you found that this is B and this is A, let's suppose, and you saw that you needed some X ml of B which you have observed. Then you say that X ml of B reacts with 10 ml of B, because the moment the reaction is complete the color changed because of some indicators, right? We will talk about this. And then you say that okay, if my X ml of B is required for let's suppose 10 ml of A, then you can find the strength of A, right? What is the percentage strength or those kind of stuff you can find. You have done this kind of thing in the labs, titrations, where you find the strength of one solution. So here I am trying to find the strength of solution B with respect to strength of solution A, right? And there are various types of titration: the acid-base titration, redox titration, gas-phase titration, complex geometric titrations, zeta potential titration, and many more. But in this case, we'll be focusing more on redox titration because that's our chapter. But before going through redox titration, let's also discuss acid-base titration. In acid-base titration, that all depends on the neutralization of acid and base. For example, in this case, we use indicators which have different colors in acidic and basic medium. For example, methyl violet, it has yellow color in acidic medium and violet color in basic medium, right? Methyl orange is red color in acidic, yellow in basic. Litmus is a good test, red in acid, blue in basic, right? Phenolphthalein color is in acid and pink in blue, pink in basic. So this kind of titration where we have acid-base titration, what we do is we react some acid and base. The moment it becomes neutral, you get different color. The moment you get acidic, you get different color. The moment you get basic, you get different color, right? So with that, you can find out whether the reaction happened or not, right? So that way, this is used. But in redox titration, it is a little different. So if you see, in this case, a known concentration and volume of titrant reacts with analyte determine the concentration. Here, analyte is nothing but a substance which is going under lysis, where you find the percentage concentration of substance, and titrant is nothing but my known region. They are of known concentration. We know the concentration of that, so that, and we know the volumes of that, so that we can it's nothing but calibrating, right? So we know this concentration of this, so we can find the concentration of this, right? This is unknown and this is known. That's the only difference. So titrant is known and titrant or analyte is something which is not known. And some of the popular titrant or reagent in the market is all these: methylene blue, which is blue. When oxidizing, when it's get reduced, it is colorless, right? Or diphenylamine, which is violet and oxidizing, and when it's reduced, it's colorless. You don't need to understand more, because in your class you don't have to understand this thing in detail, but just understand this titration is a process where you find the concentration of an unknown solution by mixing with a known reagent. There are various kinds: acid base, redox, and acid base where you take the privilege of some indicators like what you call phenolphthalein, or there are various indicators which change color on acid and base. But in redox titration, we perform our titration, and there we have indicators which change color on oxidation and reduction. If we oxidize it, it change color. If you reduce it, change color, right? So we'll take some examples for this. And This is what the redox indicator I'm talking about, right? So there are three cases in the redox titration actually. In the first case, the reagent which we use, that itself is colored. For example, MnO4 minus and I2, they itself are colored. For example, iron, if you oxidize and this MnO4 is reduced, the color change. MnO4 minus, if you see per magnet ion, it's blue in color or purple in color, and this MnO2 is pink in color. Same thing with iodine. Iodine is blue in color, but when it becomes I minus iodine ion, it is colorless, right? So the reagent itself is your color. The second scenario is the reagent is able to oxidize the redox indicators. So I have redox indicators, I have told, right? So in case where my reagent, for example, if I'm using Cr2O7 minus 2, if I'm using this reagent, right? But this reagent doesn't change color or oxidation reduction. But there are indicators, for example, diphenylamine. This will change color the moment this is oxidized or reduced, right? So this can be used. So please note, in this case, the reagent itself, they change color. Here the reagent is Cr2O7 minus 2. They don't change color, but they can change color of the indicators the moment they are reduced or oxidized, right? So that is also helpful to us, right? The third is the reagents are not able, the reagents which we are taking are able to oxidize I minus ion. See, please note here, iodine is also used as a reagent and iodine is also used as an indicator, because sometimes we use, for example, a reagent which is, let's suppose, copper. Copper is a reagent here, right, which is used for reduction or oxidation. And then if copper can oxidize I minus ion, it will change the color of I minus to I2, that is blue. So we can use it. Okay. See, the things are pretty clear. The first thing is the reagent is itself is colored. The second one is the reagent is not changing color, but reagents are able to oxidize the redox indicator. The third you see is sub part of this. I can make it as 2.1 actually, because this is same actually, but instead of using normal redox indicator, we are using I minus ion, and this I minus is a very cheap one, right? It's a very, not very costly, these are very costly ones, right? So we use a lot in industry, so that's why we have covered this spatially, but this is part of this. Actually there are two types only. One is where the reagent themselves change color, for example MnO4 minus I2 minus. The second is the reagent don't change color, but reagents can change color of the indicators, right? So indicators can be diphenyl, I minus also, since I minus is used very widely in the market, but this is applicable only to those reagents, because not all reagents can oxidize I minus ion. There are some reagents which can oxidize I minus ion, right? So this is a subset of this, because not all reagents can. Here most of the reagents can oxidize the redox indicators which we use. For the most of the redox indicators which we use, almost all the reagents are able to oxidize those redox indicators, for example diphenylamine. But if you use I minus ion, not all the reagents will be able to oxidize I minus ion. Some of them can oxidize. So in that case, we can use the cheaper alternative I minus ion, and that's why it is used in the market. So here there are two different things. One is it's cheaper, and second, not all the reagents can oxidize this. Only few of them can oxidize I minus ion. So if a reagent can oxidize I minus ion, it's better to use I minus ion because it's cheaper. Correct. But there are some limitations of the concept of oxidation number. And what is the limitation? And the limitation is pretty easy, because we have seen the concept of redox reaction, the concept of oxidation definition itself is evolving, right? We talked about addition of oxygen to addition of oxygen and removal of hydrogen. Then we talked about addition of electronegative and removal of electropositive, right? And then we talk about loss of electrons. Then we talk about increase in oxidation number, increase in oxidation number, right? Increase in oxidation number. And then we talked about electron density, right? So if you see decrease in electron density. So the first slide which we took, right, the decrease in electron density. So if you see the process, the definition of oxidation itself is evolving, it's changing, and that's the only limitation of oxidation number, because the definition itself is not constant, right? Every decade the chemists come with a new definition, and we have seen this, the history of oxidation number. Initially they told it's addition of oxygen, then they told addition of oxygen and removal of hydrogen, then they told addition of electronegative element, removal of electropositive element, and then they told loss of electron is oxidation, then they told increase of oxidation number is oxidation, and the current definition says that decrease in electron density is oxidation. Thank you. Visit examfear.com to watch free educational videos, try free online tests, get the best quality study materials, study from the best tutors and mentors, and much more. Thanks once again.